studying historical geology, what we're going to do in the semester is we're going to look at sequences of rocks like what we have here at the Grand Canyon, and we're going to read those rocks, and then that will tell us the story of our planet. Right? As a geologist, I can look down here at these rocks and I can be like, oh, there was once a big mountain range here that got eroded down. And then we look at these sequence of rocks, and in there I'm going to be able to see beaches and sand dunes and oceans and rivers and all kinds of stuff. And so the rocks are basically the chapters of history that we read in historical geology. And I know for some of you guys, it's probably been a little while since you had physical geology. And so today what we're going to do is have a brief review of minerals and rocks and a little bit about what they can tell us about Earth's history. We're going to start with minerals because minerals are what make up rocks. And a mineral, not every substance on Earth is a mineral. There are 5 characteristics that make something a mineral. Every mineral is naturally occurring. Nature has to be able to make this thing. It's not something we only make in a lab. It's usually inorganic. There are a few exceptions to that, but by and large, the majority of minerals are inorganic. It is solid, and more than just being a solid, it is crystalline. Crystalline means there's an ordered atomic arrangement. So imagine each of these little ping pong balls is an atom. Over here, this is chaotic, right? There's no orderly arrangement to the atoms. Over here, we have this repeating pattern to those atoms. So those would be crystalline. This is not crystalline. Not every solid is crystalline. For example, glass is solid, but not crystalline. And last but not least, a mineral has a well-defined chemical composition, meaning we can write a chemical formula for it. Basically, minerals are chemicals. And when we're identifying minerals, there's a lot of different properties we can use to help us identify them. There's color. I usually recommend not using color because it's incredibly variable. In fact, every one of these minerals shown on here is quartz, even though every one of them is a different color. So try to stay away from using color to identify minerals. There's also streak, which is the mineral when it is powdered. We have 4 black minerals, but 4 different colored streaks there. The way you get the streak is you have a ceramic plate that you rub the mineral against, and that will turn the mineral into a powder. There's luster, which is the appearance of light reflected off minerals. There's metallic, which looks like a metal, silver, gold, bronze, something like that. And then there's non-metallic, and you might have things like vitreous, that means glassy or silky or earthy. It's not metallic. There's hardness, which is the resistance to scratching, and we measure this on Mohs hardness scale, which goes from 1 being the softest to 10 being the hardest. And you can use these known minerals to kind of figure out where your unknown mineral fits. There's the crystal form. That's the shape the mineral takes as those little atoms all arrange themselves in that crystalline form. You can get different shapes to the mineral depending on how the atoms arrange themselves. There's cleavage, which is the tendency of a mineral to break along zones of weak bonding. So you can see sometimes minerals break. They have this one zone of weak bonding and they'll actually peel apart. Or they might have 2 or 3 or 6. They can have different numbers of these weak zones. And so you have to break the mineral to figure out what its cleavage is. Sometimes minerals don't have any weak zones of bonding, so they will not have cleavage, but they will break through fracture, and that's where you get an uneven break. Or you might get this, it's called a conchoidal fracture, where it's kind of smooth but curved. And that's a diagnostic thing for certain minerals, is their fracture. Specific gravity is, well, technically it's the ratio of the mineral weight to the same volume of water, but you can kind of think of it as density, where some minerals simply are denser than others. And then there's all kinds of special properties to certain minerals. You can have effervescence, is where it reacts to acid. You can have double refraction, which is where you get a double image projected through a mineral. Some taste certain ways, some smell certain ways, some are magnetic. There's all kinds of special properties that can be used to identify different minerals. Now, minerals have many uses in historical geology because many minerals form in unique environments. So if you find that particular mineral, you know the environment of formation. For example, certain metamorphic minerals form under certain temperature and pressure regimes. Like kyanite is always going to be at higher pressures, andalusite at lower pressures, sillimanite at higher temperatures. So that's going to tell you a little bit about the conditions under which the rock formed. Minerals tell you about the chemistry of magma or lava. Different magmas have different minerals in them. Some minerals form in oceans, some in deserts, some in big mountain ranges. So different minerals form in different places. So that helps us interpret Earth's past. And many tell us other parts of Earth's story as well. For instance, some minerals are magnetic and can capture paleomagnetism, which helps us figure out where continents were located in the past. And other minerals contain radioactive isotopes, which can help us figure out the ages of different rocks. Those can actually tell us exactly when certain events happened. So minerals have many uses for us when we're interpreting Earth's history. Now, earlier I said those minerals go into making rocks. Well, different, and before I go into that, let's look at what rocks are made out of. Usually, they're going to be our silicate minerals. Those are the most abundant ones. So most of the rocks you pick up outside, or a handful of dirt or something like that, is going to have silicate minerals in them. And those silicate minerals include things like quartz and feldspar and micas, muscovite and biotite. Those get peeled apart nicely. Amphiboles, pyroxenes, olivine, and clay minerals. So most of the rocks that you see outside, those are going to be the minerals that you'll find in them. But there are some other groups of minerals that are important. For instance, if we're dealing with limestones and those sorts of rocks, those are made out of carbonates. Carbonates include calcite, like that, dolomite, and aragonite. You have evaporite minerals that are formed from the evaporation of water. That includes things like halite, gypsum, which we see here, and a mineral called anhydrite. And then there's some other minerals that are not in the silicate group of minerals or the carbonates or any of these others. Other non-silicate minerals are important in ore deposits, like where we get some of our copper and iron and other resources from. And again, those form under very specific conditions that can tell us a little bit about the history of our planet. So when we're looking at those minerals, I said they make up rocks, and there are three basic rock types. Our igneous rocks come from molten rock, from melted liquid rock that cools and becomes solid. And sometimes that igneous rock cools and becomes solid underground. Those are the intrusive or plutonic igneous rocks. And those can be things like granite, diorite, gabbro, or peridotite. And exactly which one you have depends on the minerals inside it, and these different igneous rock types form in different geologic environments. Now, if that magma makes it to Earth's surface and erupts out of a volcano, then it ends up being an extrusive or My cat is watching birds out the back window, and he's letting me know he's upset that he can't catch them. So anyway, if that magma erupts onto Earth's surface out of a volcano, we call it an extrusive or volcanic igneous rock. And there we might have rhyolite, dacite, andesite, or basalt. And again, the minerals inside tell us which type of rock this is, and depending which composition we have, they actually erupt out of the volcanoes in different ways. Some are very explosive, some not so explosive. Other extrusive igneous rocks that can tell us a bit about Earth's history can include things like tuff, which is created in a violent explosive volcanic eruption, obsidian, which is volcanic glass, or pumice. Now, what do these igneous rocks tell us about Earth's history? How we use them in historical geology? These were the first rocks to form on our planet. These are what we usually use in those paleomagnetic studies, because those have those magnetic minerals in them. They're also what we use for geochronology, which is when we figure out when different events happened. They can tell us a bit about plate tectonics, because different igneous rocks form in different plate tectonic environments. Some form in rifts, where others form at subduction zones. Large volcanic eruptions can have a major effect on Earth's climate system and life. So igneous rocks and where they're formed and when they're formed can really tell us a lot about how our Earth has developed over time. Now, our second group of rocks are the sedimentary rocks. Sedimentary rocks are formed by the weathering and erosion of older rocks. And what happens? Older rocks get broken down, they get eroded, they get carried off to some other location. That broken up material gets dropped off or deposited. And so this sediment gets deposited in layers, which we call strata, at Earth's surface, and then it gets turned into solid rock. That's what we call lithification, where we go from this basically like loose material to solid rock. And we break down sedimentary rocks into two basic groups. We have the clastic ones that are the solid pieces of weathered material. So this is going to be like the sand that you see on the beach. And you could have a conglomerate or a breccia. And this is where we have big pieces. And if it's a conglomerate, it's big round pieces. And if it's a breccia, it's big angular pieces. You could have a sandstone. Sandstones are made of, well, sand-sized pieces. You can see the little pieces in there. They're small, they're not big. This is zoomed in on a sandstone. There's all these little sand grains in there. This is what a sandstone looks like in outcrop. When we talk about outcrops, we're talking about places where solid rock is exposed at Earth's surface. That's a very typical sandstone outcrop. We might also have rocks made of smaller particles, so small that you can't see the individual particles unless you look at them under a microscope. If it's made of really, really small pieces, we'll either be looking at a siltstone, a claystone, or a shale. Well, what's the difference? Siltstone and claystone have kind of a blocky appearance like this. Shale breaks into nice thin layers. We describe that as being fissile breaking into thin layers. So claystone or siltstone versus shale. In outcrop, exposed at Earth's surface, this is what the siltstone, shale, claystone typically looks like. in sedimentary rocks, we also have chemical sediments. Chemical sediments come from the parts of rocks that got dissolved in water and then carried away before it gets dropped off. And the most abundant chemical sedimentary rock is limestone. Many limestones are fossiliferous, like this one. Not all of them are, but many are. You can also find fossils in shales and sandstones in any sedimentary rock, but oftentimes in limestones you do find fossils like that nice coral fossil over there. Other sedimentary rocks include things like dolomite and gypsum. This is what gypsum often looks like. That is an evaporite. So that formed from the evaporation of water. You also have rock salt, which is halite. That is me standing, this is Death Valley when there's water in it. This was like March of 2005. The winter of 2004 to 2005 was really, really wet. Lots of snow fell in the mountains around Death Valley. And then come springtime, all that snow melted and all that meltwater went into Death Valley. There's like 12 feet of water in there. There's some dude kayaking out in the middle of Death Valley. But basically that water was not fresh water. That was very, very salty. And so as that all evaporated, see this white in front of me? As all that water evaporated, that precipitated rock salt, or halite. And so that would tell us, if we find things like the evaporites, gypsum and halite, that tells us we were probably in a very dry environment where water was being evaporated. Now, last of our sedimentary rocks, we have organic sedimentary rocks. Organic rocks are made from, well, organic material that did not decay. And basically that's coal, like this, right? Coal is our organic sedimentary rock. There you can see some more bits and pieces of coal. The big thing about sedimentary rocks and historical geology is these things preserve fossils, so they're going to give us the insight into the life that lived in the past. They also give us clues to paleo environments. Now, anytime you see that prefix paleo, that means ancient. And so paleo environments are ancient environments. And the way that these sedimentary rocks give us clues into paleo environments is because certain rocks, sedimentary rocks, form in certain environments. Like this coal does not form everywhere. This forms in like swampy areas and bogs, places where you have stagnant, standing water. And so you wouldn't expect like, oh, we have coal from the desert, because number one, you don't have a lot of organic material in the desert, and you don't really have swampy areas where that's going to be preserved. So you know you're going to be like, oh, it's going to be a swampy area, like maybe southern Florida or southern Louisiana. That would be a place where coal would be forming today. But you know, different environments, you get different sedimentary rocks. And this diagram is simply showing that, where for instance you get evaporites in the desert, or you get limestones in reefs, or you get things like conglomerates in glacial areas. And so these sedimentary rocks give us great insight into what the ancient environments looked like.